Welcome to the long-awaited and much anticipated, and I'm sorry for the delay, video about the dot product. The list of little details that we're going to look at in this video regarding the dot product the list is long, so I'm not going to try to give you the list. We're just going to get right into it. Just getting my microphone situated, and all right, let's see what's to be seen as far as vectors and the dot product. The first thing we're seeing here is the definition of the dot product. And if we take two vectors, v and w, and they're defined in this first blue box for us, v is equal to a1i plus b1j, and w is there with different coefficients on I and j. Then the dot product, v dot w, is equal to the product of the I coefficients plus the product of the j coefficients. And of course, just when I finally get to start getting something done, who comes in and steals the show? Yes, we know that you're beautiful and adorable. What are you seeing? It's not like you've never been here before. You should have all this figured out already. Good for so many things, but math's not really one of them. Let's see what it is that we can do with the dot product as far as some properties that allow us to do some maneuvering. There's a commutative property. It looks like u dot v is equivalent to v dot u, which is certainly true because of this plus sign at the top of your screen. The a's, the product of the a's plus the product of the b's, you could switch those around, the a's and the b's. This could be a2, a1, and b2, b1, no problem. We'd get the same result. In number 2, u is being dotted. Now remember, u and v and w, these are all vectors, and you can think of them in that format. AI plus bj. So we can add a couple of vectors first and then dot it with a third vector, the result of that vector addition, or we can distribute the dot product over addition and find the sum of u dot v plus u dot w. We can dot with the 0 vector, and the result will be, let me ask you, if we do 0 vector dotted with the v vector, whatever v happens to be, the 0 that's on the right-hand side of that equal sign, is that another 0 vector, or is that the number 0? Remember that at the top of your screen, this says a1, a2 plus b1, b2. All 4 of those values are numbers, so it's the sum of a couple of products. The result of a dot product is going to be a number. So in number 3 of these properties, the 0 that you're seeing on the right-hand side of the equation is the numeral, the integer 0. It's a constant. It's not a vector. Number 4 shows us that if we take v and we dot it with itself, we end up getting the magnitude of v squared. Interesting, and that will come up a little bit later. And in number 5, c is a scalar, so it's just a number. And we can multiply that into a vector u and then dot it with the v vector, or we could, in here, we could do u dotted with v first and then distribute multiplication by a scalar. Or, and this is really interesting, we could take this scalar c and multiply it into vector v first. That's what we're seeing right here. And then we could dot the result of that with the u vector. And all of those combinations would yield the same result, the same number. So let's just try a couple of them in order to start getting a feel for these, and then you're going to do some other practice problems and homework problems and look at some other examples and continue to get more comfortable with these. But let's just do a little bit of an introduction. So let's do v dot w. And remember, that's the product of their I coefficients. So this is going to be a 7 times a negative 3 plus the product of their j coefficients. That's a negative 2 times a negative 1. And so we get 21, but it's negative. And we have a double negative there, so it still ends up being addition with 2. And we get a final dot product value of negative 19. Now, so far, that negative 19 doesn't seem very valuable. We're just happy that it's a correct answer. And that's totally fine for the moment. Let's also go ahead and do v dotted with itself. That's equal to 7 times 7 plus negative 2 times negative 2. So really, well, I sounded more excited than I should have been just there. We could write this also as 7 squared plus negative 2 squared. And that looks a lot like a squared plus b squared. And you could think of it that way. The other thing that we normally think of when we think of a squared plus b squared is that it equals c squared. So that would be the Pythagorean theorem. And in fact, that's pretty much how we were evaluating the magnitude of a vector, is we were taking the square root of a squared plus b squared. Now, if we squared both sides of that little equation, we would end up with magnitude of v squared equals a squared plus b squared. So that's what's happening in number 4 up here. When we take v and we dot it with itself, we do indeed end up with a squared plus b squared. And what does that equal? It equals c squared, which in the world of vectors is c is the magnitude of the vector, and so c squared is the magnitude of the vector squared. All right, so 49 plus 4 equals 53. Another seemingly arbitrary value that results from performing the dot product. But at least it did get us off of the first page and onto the second page. Let's see. So we're dotting with a sum. We've got a constant value that's going in there. Let's do these two, and then I think we'll move on. In the first example, let's add u and w first. I think I'll write this as vector v. I'm going to put v in parentheses. Maybe I'll put an equal sign to the left of it. And I'll put v in parentheses, so that's 3i plus j. And then I'm going to put a dot right here. Can you imagine? We transitioned when we were in high school, maybe, some of us. We were still using a little x to represent multiplication, and then at some point we got transitioned to using a dot to represent multiplication. That's when we're using something, right? This might just, this says 5v. We know there's multiplication happening in there. We don't even write a symbol. But all of a sudden, this dot as a multiplication symbol can become confused with the dot product when you're working with vectors. So just be careful that you're keeping an eye out for what the dot is supposed to mean depending on the environment that you're operating in. So here it's definitely a dot, and I'm going to put in square brackets the sum of these two vectors. So I have vector u, which is 2i minus j, plus vector w, which is I plus 4j. And inside these square brackets, I'm going to combine like terms. So I'm keeping the 3i plus j out front. We're still going to do a dot with, and then I'll write the results of my vector addition inside these square brackets, but I'm going to put the result in parentheses. The 2i plus the 1i makes 3i's, plus, and a negative j plus a 4j makes 3j. And now I have, excuse me, a dot product that I think we can fit right in here. And so let's see, the 3i and the 3i, so those 3's get multiplied together, plus the coefficients on the j vectors, so that's a 1 and a positive 3. And that's equal to 9 plus 3, which is equal to 12. The results of these dot products don't even hardly seem to have a pattern yet. I don't know if you're even looking to try to find one, but I'm not seeing one yet. And we could take 5 and multiply it into vector v. Let's do this one quickly. I'm not going to write out all of the steps. I'm going to multiply the 5 into the v first. So there's 5 and then 3i plus j. We're going to be dotting that with w, which is I plus 4j. Let's distribute the 5 in. I'm going to work my way from left to right across the page on this one. So my new first vector becomes 15i plus 5j. We're going to be dotting that with I plus 4j. When we perform the dot product, we'll take the I coefficients, that's the 15 times a 1, and we'll add the product of the j coefficients, which is a 5 times a 4. So we have 15 plus 20 equals 35. And the lack of a pattern continues for the result of the dot products. So here, these are just more examples, and they actually relate back to the examples that we've just looked at. This is, I think you can figure out how to do v.u on your own now, and v.w. Those are both going to result in numbers, and you can add them together. And what should you get when you add them together? Let's see if we can write, let's see. Right here, right when I disappear, that where it says v.u plus w, if you exercise we were sort of candidly calling it the distributive property of dot products, if you distribute the v to the u and the w, you get this down here, the v.u plus v.w. So the result of performing this problem in the bottom left corner of your screen should be the same as the result of 12 that we got from doing the problem that it's in the top left corner of the screen. What else is happening down here? 5 times v.w. That's the same as or equivalent to doing the problem in the top left corner of your screen and multiplying by the 5 first and then performing the dot product. Just here we're going to do the dot product first and then distribute multiplication by 5. So the answer for this problem in the bottom left corner of the screen should be 35. So work those two out on your own and see if you get the answers of 12 and 35. Well, we survived pages 1 and 2, and now we're going to sort of mess things up a little bit by giving you an alternative formula for the dot product. Here we see some utility, though, because a theta value comes in. So v.w on the left-hand side of this formula is a number. We've talked about that. We've seen results like 12 and 35. And it's equal to, or equivalent to, taking the product of the magnitudes of v and w and then multiplying by the cosine of the angle between those two vectors. So all of a sudden, we could use magnitudes in order to figure out the angle measure between two vectors. Why I did that with my hands while I was talking, I don't know. I have to do something, right? It gets boring just sitting and talking to a camera after a while. All I have to keep me company is a little postage stamp version of myself in the top corner of the screen. The same one you're looking at right now. If we take this equation and we solve it for cosine theta, dividing both sides of the equation by the magnitude of v and the magnitude of w, then we get this equation. And if we really wanted to solve for theta, we could take the inverse cosine of both sides of that equation, and we would get this equation. Wow. It's a little intense, but I'm glad that you are here with me right now, seeing how, I suppose, we came up with this really weird formula. Doesn't it feel better to know that it comes from this really weird formula? So helpful, right? So let's try to find the angle between V and W. This should be very easy. We know that theta is going to equal the inverse cosine of V dot W divided by the magnitude of V and the magnitude of W. So we need to figure out the three components that are inside of this inverse cosine function. So let's start with that. V dot W is equal to 1 times 4 plus 2 times negative 3. That is equal to 4 minus 6, which is equal to negative 2. So we'll use that in the numerator, and then we need the magnitude of V. That's equal to the square root of 1 squared plus 2 squared, which is equal to the square root of 5. We also need the magnitude of W, which is equal to the square root of 4 squared plus negative 3 squared, which is equal to the square root of 25, which is equal to 5. So these are the three components that we need to go into our inverse cosine function. So let's keep moving. Theta is equal to cosine inverse of, I'm just going to write these numbers in. I'm not going to write down that formula that's at the top of the screen, top right corner of the screen. If you want to copy that into here first, V dot W over mag V mag W, and then another equal sign, and then you want to start filling in the blanks, that's fine. I don't have all day though. I'm just going to plug it in. So our numerator is the negative 2. And our denominator, magnitude of V is the square root of 5. And the magnitude of W is 5. If you'd like to put those in parentheses so that it's clear that they need to be multiplied together, that's a good idea. I'm going to type this into my, I don't know, I've got both calculators. I suppose we could do both. I think typing this into the graphing calculator is pretty straightforward, so let's do that one first. I'm going to hit mode and make sure that I'm in degree mode, and I am already. And I did that because we're finding the angle between V and W, so the answer that my calculator kicks out is going to be an angle measure. And angle measures in radians, in decimal format, don't mean much to me. I don't really want to have to decipher what that is, so I'm going for degrees. That'll make it pretty clear what quadrant I'm in at the very least. So let's type in inverse cosine, and a set of parentheses is already open for us. I'm hitting the negative button near the bottom right corner of the screen, not the minus button, but the negative button, and then a 2, and then divided by. Then I'm going to open another set of parentheses. I will type the square root of 5, and then I'm using a TI-84 plus, so then I have to hit the right arrow key near the top right corner on the little roundabout of arrows, so that I come out from under the square root symbol, and then I'll hit the multiplication button, so times 5, and then I'll close parentheses, and let's see, terrible. Why is it that it's always too bright? Can I change it quickly? Pretty quickly. Let's see about this. Any better? I did darken it, I swear. Was it better when it was tilted this way? It's hard to tell if it's even in focus from where I'm sitting. We gotta get just the right distance away. Maybe you could zoom in on that. I really need to get an emulator. So finally, let's hit enter. and I got 100.304 degrees. .305 if you round it. Alright, that was exciting. Let's see if it's relatively easy to get this answer on the scientific calculator. Not everybody is so fortunate to have a graphing calculator. I'm double checking my scientific calculator. It's the TI-30XA with the little green second button in the top left corner. I'm going to type in, well, first I made sure that I'm in degree mode. If I'm not, I need to hit the DRG button a couple of times maybe until DEG appears on the screen. And then I'm going to hit the number 2 first. Then I'll hit the plus or minus button. Mine's in the bottom right-hand corner so that my screen actually says -2. And then I will hit divided by 5. And then I'm going to take the square root, so hit the square root button, then hit equals, and you should have -0.08944, etc. That is -2 divided by the square root of 5. I will leave that number, that terrible decimal, on my screen. I hit the division button again, hit 5, hit equals, and I got -0.17888. That's just the fraction that's inside the inverse cosine function. So now let's do inverse cosine. I'm going to hit the second button first, then I'll hit the cosine button, and I got 100.3048, which rounds up to 305. So it worked. It's doable on both calculators. Takes a little bit of practice, I think a little bit more practice on the scientific calculator, but both of them will work. So we can tell if two vectors are parallel if the angle between them is 0 or 180, or multiples of 0 or 180. So 180, 360, 540, 270, the negative version of all of those. If two vectors are pointing in the same direction, or if they're pointing in opposite directions, we consider them to be parallel. When two vectors are parallel, they are scalar multiples of each other, right? If you take a vector and you multiply it by -2 or positive 3/5 or positive 7, multiplying by those kinds of numbers, those numbers are considered scalars. And if it's a negative number, it's going to switch the direction of the vector. If the angle between two vectors is 90 degrees, however, or pi over 2 radians, we say that the vectors are orthogonal. And we're using the word orthogonal instead of the word perpendicular. I suppose the same way we transitioned you from using a little x to represent multiplication, and we transitioned you to using a little dot for multiplication, here we're transitioning you away from using perpendicular and into the use of this word orthogonal. As I recall, and it's been a little while now, I don't think I really came to an understanding of there being a distinction between the terms perpendicular and orthogonal until I was in Calc 3. Maybe I saw it somewhere in Calc 2, definitely didn't see it in Calc 1, but when you're in three-dimensional space and you've got things that are perpendicular to things sort of floating around in the three-dimensional plane, as I recall, that's where the idea of things being orthogonal made a little bit more sense to me. If you're going that far. So we don't need to dwell on it too much, but I am going to continue using the word orthogonal. So here we see that if we take V and we dot it with W, that's equivalent to mag V times mag W times. If they are orthogonal, then the angle measure between them is 90 degrees, so we're multiplying not just by the cosine of theta, but by the cosine of 90 degrees. Of course, the cosine of 90 degrees is 0, so I don't care what the magnitude of V and W are. When we multiply it by 0, we're going to get 0. So this, on the far right-hand side of your screen, this equaling 0 only occurs if this angle measure is 90 degrees, so that the cosine of 90 degrees ends up being 0, giving us this 0 value. So if the angle measure is 90, the dot product will be 0. If the dot product is 0, then the angle measure must be 90. The fact that we can say that sort of forwards and backwards, vice versa, anyway, forwards and backwards, and it holds true 100% of the time, whether we say it forwards or backwards. V dot W, 90 degrees, dot product is 0. If the dot product is 0, theta must be 90 degrees. When you can say it forwards and backwards like that, that's sort of a bidirectional statement. We end up using this very specific language, if and only if. So two non-zero vectors v and w are orthogonal if and only if their dot product is 0. The if and only if means that you could basically read the sentence from right to left. V dot w equals 0 if and only if two non-zero vectors v and w are orthogonal. In other words, meeting at a 90-degree angle. Let's try to determine whether these vectors are parallel, in which case they are scalar multiples of each other, or perhaps they're orthogonal, in which case their dot product will equal 0. Or if both of those fail, if it's neither parallel nor orthogonal, there's no other choice, no other specific option, so we just go with neither parallel nor orthogonal. So let's see, can we take V and multiply it by something and turn it into W? I think we can. I think that if we take 3 and multiply it by vector V, that will equal 3 times negative 2i plus 3j, which is equal to negative 6i plus 9j, and hey, that's equal to W. So the fact that a scalar times vector v ended up equaling vector w means that these two vectors are parallel. So if you've written down exactly what I've written down, including the highlighting of the 3v and the w, when you read through these notes again later, that might not be enough to help the conclusion of parallel to make sense. So it might be to your advantage to write down some other information over here in your own words that reminds you later that since we were able to take one of the vectors and multiply it by a number and get the other vector, since we were able to do that, we know the vectors are parallel. Okay, in your own words, put something down right over here. Next, so I see how this is negative on the I term, negative on the I term. So if we were going to take V and scale it up to turn it into W, we would have to multiply it by, well, in this case, we'd have to multiply it by 3, because negative 2 times 3 equals negative 6. However, positive 3 times a positive anything is not going to equal a negative. So it turns out these are not scalar multiples of each other. And you could write a little note. 3v equals negative 6i plus 9j, which does not equal w. Therefore, not parallel. It's not a bad note to include. And then we need to try the dot product to see if they're perpendicular. So underneath that, see if you can fit in the dot product. V dot w is equal to -2 times -6, that's the product of the I components, plus the product of the j coefficients, which is a +3 times a -9, and that is equal to 12 minus 27, which does not equal 0. I don't even care what it equals. The only thing I care is that it doesn't equal 0. If it equaled 0, then our vectors would be perpendicular. However, not orthogonal. Ugh. I said I was going to keep using that. Orthogonal? Orthogonal. Okay. Not parallel and not orthogonal, therefore our answer for this one is neither. Well, since we've gotten a parallel and a neither, my hope is that this last one's going to be very easy and that we can calculate the dot product, get our 0, and keep going. Let's try the dot product right away. V dot W is equal to the product of the I coefficients, that's a -2 times a -6, plus the product of the j components, we have a 3 times a -4, that's equal to +12 plus a -12, which is like subtracting 12, which is equal to 0. Yay! Therefore, orthogonal, formerly known as perpendicular. I'm just staring at these you-tried examples and doing them in my head real quick so that I can tell you what the answers are, so that if you want to work them out on your own, you can work them out on your own. -5, -20, not orthogonal. Multiply by -5. So they're parallel. -5 is the key on the first pair of VWs. On the next pair of VWs, those are actually also orthogonal, or also parallel, because I think you'll find that, oh no, sorry. Those are orthogonal. The first pair of VWs was parallel. The next pair of VWs is orthogonal. You'll have 8 minus 8, giving you 0 for the dot product. But try those on your own. And then I've decided I am going to take this section about projections and components, and then a last little subtopic that comes after that where we talk about work, which is equal to force times distance, and I'm going to put those into a second segment video. So if you would be so kind, if you're ready to move on to these next couple of topics, to please click the little box that is below me and follow me on over to that next segment. The explanations that are in there are a little bit detailed, and I go very much into detail about sort of why the next formula is what it is. So that's why the video is a little bit longer, and I'm going to turn this into 2 segments, and I hope to see you there. Thanks so much. Oh, and the iPad has ditched us. Good timing. See ya.